Good morning. Today we will present the project of Sensor and Instrumentation System. The title of our project is Flow Monitoring and Alert System using IoT. This project prepared by Pavitra TP22063, Aravin TP22065, Tangguanchan TP23034, and Akram HA21036. Next, in introduction, flooding is a major hazard. Here, many areas still rely on slow, manual monitoring, which lead to delay warning and increased risk. To solve this, our project utilizes IoT technology to create an automated real-time flow monitoring system. This ensures early detection of rising water level and provide immediate alert to protect residential area effectively. After that is objective and scope. The main objective of the project is to develop a real-time flow monitoring system using the ESP32 to provide timely alert via physical alarm and the Blynk mobile app. The scope is focused on small-scale detection suitable for residential area and the drainage system, prioritizing immediate local warning and sensor integration over large-scale weather forecasting.
So for the hardware overview, for microcontroller we use ESP32 because it has Wi-Fi, and we're gonna connect that with our Blynk app. And then for sensor, we use three sensors, which is LDR light sensor to detect sunny or cloudy conditions, and then we have rain sensor to detect rain intensity, whether it's light rain or heavy rain. And then we have water level sensor to measure water heights. And then for actuator, which is the outputs, we have LCD to display status text, and then we have servo motor to simulate the flood barrier between 0 degree until 90 degree. And then we have buzzer to sound the alarm for warning or danger.
This slide shows the actual hardware prototype of our system from different angles. The front view shows the LCD display and the flood barrier mechanism. When the water level rises, the barrier opens, which can be seen clearly in the barrier open front view. The side view highlights the circuit implementation, where all sensors, the ESP32 and output devices are physically connected using jumper wires. The top view provides an overall view of the complete setup, showing how the components are arranged compactly. This prototype was fully functional and used for all the testing and demonstration in this project. This slide shows the circuit diagram of flood monitoring system. The ESP32 is placed at the center and acts as a main control unit. The light sensor, rain sensor, and water level sensor are each connected to separate analog input pins, allowing the ESP32 to read sensor value independently. The 12C LCD is connected using SDA and SCL pins to reduce the number of GPIO pins used. The servo motor is connected to the digital PWM pin to control its rotation angle, while the buzzer is connected to the digital output pin for alert activation. All components share a common ground to ensure stable operation, and the ESP32 used its built-in Wi-Fi to send data to the Blynk application for real-time monitoring. Now, next slide is about how the system works, data acquisition. The ESP32 continuously reads analog data from all the three sensors in real time, processing logic. Each sensor uses its own threshold values. For the light sensor, value is 1500 indicates sunny condition, while values above 1500 indicates cloudy conditions. The rain sensor classifies rainfall into no rain, light rain, or heavy rain based on surface wetness. The water level sensor determines the flood state, which is safe below 900, rising between 900 to 1399, and flood when the values exceed 1400. Now let's go to system response output, which is based on the processed sensor data. The system responds automatically. The LCD displays live information showing the current light condition, rain status, and water level state. During the rising buzzer produces the intermittent warning sound, which is T, 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 which can be heard in the demonstration video. When the flood condition is detected, the buzzer switches to continuous sound to indicate the serious danger. At the same time, the servo motor rotates to 90 degrees during rising or flood condition to stimulate a flood barrier opening. When the water level returns to a safe state, the servo rotates back to 0 degree, closing the barrier.
So today I'm gonna talk about the IoT integration of our system. The system continuously sends sensor data to the Blynk cloud every second and enabling the real-time remote monitoring. Through the Blynk dashboard, user can easily view the live readings of our water level, the rain intensity, and also the light conditions using a graphical gauges. The system also provides immediate status updates, clearly indicating whether the area is in a safe condition or not, or experiencing flood. Overall, this integration allows users to monitor the flood-related parameters anytime, anywhere using a mobile application, improving the awareness and early response. As we all know, prevention is better than cure. After that, the app configuration for the light sensor indicator. This gauge widget is configured using a visual data stream. We want to display the sunlight intensity in real-time live. When the sensor is valued between 0 and 1505, the system indicates sunlight and the gauge turns yellow to indicate the bright environment. When the value increases from 1505 to 3500, it represents the cloudy or low light conditions, and the gauge changes to gray, suggesting it might be possible rain. This visual color-based indication helps users quickly understand the environmental conditions without needing to interrupt numerical values. In this slide, we can see the configuration for the rain sensor indicator. The gauge widget is connected to a virtual data stream V2, which receives real-time rainfall data from the sensor. When the sensor value is between 0 and 1804, the system detects heavy rain and the gauge turns into red to indicate strong rainfall. Values between 1804 and 3362 represent light rain, shown by a yellow color for easy identification. Lastly, when the value rises to the range of 3362 to 4100, it indicates no rain and the gauge turns green to show dry conditions. This color-coded display allows users to quickly assess rainfall intensity at a glance. In this slide, we can see the details of how we configure the Blynk app interface to utilize the virtual pin V3 in real-time water levels. First, the green zone is from 0 to 900. It indicates a safe and normal water level. Second, if the water reaches between 900 and 1410, the gauge turns yellow. This serves as a warning that water levels are rising. Finally, anything up from 1410 up to the max value of 3000, it turns red, alerting the user that a flood condition has been detected and it is rising.
For system demonstration, for the sensor validation, we want the light sensor to accurately distinguish between sun and the cloud. And then for the rain sensor, we want it to be successfully detect the rain intensity levels. And for the water sensor, we want it to identify safe rising and flood states correctly. And for the system stability, we want the system to run continuously without crashing, and it must updates to LCD with a real time to LCD and mobile app. So as you can see from the Blynk app, which is the GUI at the sunlight part, when my friend put the light on the sensor, the gauge turns yellow, which indicates that it is a sunny day because there's a sun. And then when it moves away, the light is moved away, the gauge gonna turns gray. That indicates a cloudy or maybe gonna rain. So that's just show how our system works for the light sensor. For this rain sensor, as you can see at the first video, at the first starting the video, the gauge is colored green because it indicates that it's a dry situation where it's not raining, it's just a sunny day. So after that, my friend spray some waters on the rain sensor, and the gauge eventually started to change to yellow color. So that indicates the sensor sense that it started to mild raining. And then after that, my friend pour some more waters on the sensor, and the gauge turned to red color, which indicates that it's a heavy rain. All right. So for the water level sensor, we have three stages also, which is the first one is starting at at the start of the video. As you can see that the gauge is green color, which means the water level is now at the normal level. So it's safe for everyone. And then when my friend adds some more water, the water level start to rising, and the gauge turn to yellow color. And after that, my friend adds some more water. Now the water level is higher than before, and it's at uh, a risky or a danger level. So it might be flooding right now. Um, so the gauge turns to red color, and then the servo motor is activated. It in real life situation, we can say that it's a flood barrier, and also the buzzer also activate. That is indicates that it's sounding everyone that alarming everyone that everyone must go to some sort of safe place.
Last is conclusion and future work. In conclusion, we successfully developed a functional prototype that integrates ESP32 hardware with IoT technology for effective real-time flow monitoring. Moving forward, the system can be improved by adding SMS or WhatsApp alert for critical notification, implementing solar power for standalone outdoor use, and enclosing the device in a waterproof casing to ensure long-term durability in real-world conditions.